Hello student, myself name is Prabhakar. Welcome to Process Control lecture series. In my previous lecture, we discussed the floating control mode. That means that mode is the type of discontinuous control mode. Now we start continuous control mode. So which are continuous control mode? We know mainly three continuous control mode: proportional, derivative and integrated. So now we start in this lecture about the proportional control mode. So in this lecture we discuss the proportional control mode. So before starting that, we understand what are the limitations of two position and multi-step modes. So we discuss the limitation of two position and multi-step modes. So first one is the two position mode had the controller output of either 100% or 0% depending on the error being greater or less than the neutral zone. So this is the first one limitation of two position control mode. In multi-step mode or in the multi-step mode, more division of controller output versus error are developed. So these are the two main limitations of two position and multi-step mode. So how we can overcome this limitation and what is the solution for this? So the solution is proportional mode. The natural extension of the concept is the proportional mode, where a smooth linear relationship exists between controller output and error. So this is the solution for the limitation. Now we start proportional control mode. In this mode, a linear relationship exists between the controller output and error. That means in this mode, the relation between the controller output and the error is linear. For some range of error about the set point, each value of error has unique value of controller output in 1-to-1 corresponds. The range of error to cover the 0% to 100% controller output is called proportional band. Because the 1-to-1 corresponds exists only for the error in this range. That means here we get 1-to-1 output for the error. That means controller output for the error, but specific range, and that range is known as the controller range or the natural band. The analytical expression for this mode is given by P is equals to KP EP plus P0. This is the analytical expression for the proportional mode. Now here, the Kp indicates the proportional gain between the error and controller output, and P0 indicates the controller output with no error in percentage. Now direct and reverse action. We already know what is the direct action and what is the reverse action. So here we discuss in terms of the proportional control mode. So the equation 1 in my previous slide represents the reverse action. Now question under how it represents the reverse action? So the answer is because the term KP EP will be subtracted from the P0 whenever the measure value increase the above set point, which lead negative error. That's why it operates in a reverse action. The equation for the direct action can be given by the putting the negative sign in front of correction term KP, EP. So it becomes the direct action mode. Now we understand by help of this figure. A plot of the proportional mode output versus error for equation 1 is shown in figure. So here we plot one graph, the output versus the error. So in this figure, P0 has been set to a 50% and two different gains have been used. That means you can see the graph is plot for the G1 and G2. These are the two different gains. It can be observed that proportional band is depend on the gain. So you can see in the graph, as the gain changes, then the proportional band is also changed. That means what? Proportional band is depends on the gain of the controller. The higher gain G1 leads to a large or flat response but narrow band of error. That means if we increase the gain, then we get larger or fast response. But at that time, the band becomes the narrow. Same as opposite, on the other hand side, a low gain G2 leads to small or slower response, but a wider band of error. So this is the operational characteristic of the proportional control mode. In general, the proportional band is defined by the equation PB is equals to 100 upon KB. So here PB indicates the proportional band and KB indicates the gain of the controller. Now we summarize the proportional control mode. So if the error is 0, the output is constant and equal to 0. That means from the equation number 1, we can see if our error is 0, so at that time the controller output is constant or equal to P0. If there is error, for every 1% error, a correction of Kp% is add or subtract from P0 depending on the sign of error. That means if sign is negative or positive, error sign is negative or positive, we add and subtract the gain accordingly. There is a band errors about the zero magnitude PB within which the output is not saturated at 0% or 100%. So this is the summary of proportional control mode. Now offset error. So what is offset and why we study offset error in proportional controller? So now we start. So what is offset? Proportional control alone is unable to eliminate the offset error, which is the difference between the desired value and the actual value, that means SP minus PV error, as it requires an error to generate an output. An important characteristic of the proportional control mode is that it produces a permanent residual error in the operating point of the control variable when a load change occurs and is referred to as offset. It can be minimized by larger constant Kp, which also reduces the proportional band. That means if we want to decrease or minimize the offset error, so we increase the gain Kp. But if we increase gain, then the band becomes narrow. So this is the offset error. Now we discuss about the advantages of proportional control mode. So first one advantage is easy to implement. Now next one is low cost. Third one is easy to tune the proportional constant. That means we can easily tune the proportional constant. So this is the also advantage of proportional control mode. Now we discuss about the disadvantages, or we can say limitation of proportional mode. So which are that? So first one limitation is response only change in error. That means response change when the error is come. Error cannot be reduced to zero. Control value cannot reach the set point. So this is the biggest limitation of proportional control mode. That means in this mode the error cannot be reduced to zero. We cannot eliminate totally error. So this is the limitation of proportional control mode. And last one is fine controlling is not possible. Now we discuss about the application of this proportional controller. So first one is whenever there is one-to-one correspond of controller output is required with respect to error, change proportional mode will be ideal choice. The offset error limit the use of proportional mode, but it can be used effectively whenever it is possible to eliminate the offset by resetting the operating point. That means we can use the offset error is one problem, but we can use this when the elimination of offset is possible. Proportional control is generally used in a process where the large load changes are unlikely or within a moderate to small process lag time. That means we can use the proportional band where the process lag is small. If process lag time is small, the PB, that means proportional band, can be made very small with a large KP, which reduces offset error. If KP is made very large, the PB becomes very small, we know, and proportional controller is going to work as on-off mode. High gain is proportional mode cause oscillation of the error. That means if we increase the gain beyond some limit, then there is the error or some output is that means the oscillation is produced in the operation. Now we take example. Consider the proportional mode level controller system of figure. While A is linear with a flow scale factor of 10 meter cube per hour per percent controller output. The controller output is normally 50% with a constant Kp is equals to 10%. A load change occurs when a flow through valve B changes from 500 meter cube per hour to 600 meter cube per hour. Calculate the new controller output and offset error. So here we have given the Kp, that means the gain is the 10%, and we have to find out the controller output and offset error. So now we start procedure. Certainly valve A must move to new position of 600 meter cube per hour flow or the tank will empty. This can be accomplished by 60% new controller output. How? Because QA is equals to 10 meter cube per hour in percentage into 60%, so we get 600 meter cube per hour. That means if we increase the output from 50% to 60%, then we can control the system for the 600 meter cube per hour flow rate. Now this is a proportional controller. So we have P is equals to Kp into Ep plus P0. With the nominal condition P0 we know 50%. Thus Ep is equals to P minus P0 upon Kp. So we have the value of P, P0 and Kp. So we get Ep is equals to 1%. That means offset error is 1%. So the 1% offset error occurs because of the load change. Now we see second order example. For a proportional controller, the control valve is a process temperature with a range of 50% to 60, 50 to 130 centigrade and a set point of 73.5 centigrade. Under the nominal condition, the set point is maintained with an output of 50%. Find the proportional offset resulting from a load change that requires a 50% output if the proportional gain is 0.1%, 0.7%, 2 and 5. So here we have given the temperature range is between 50 to 130 centigrade. Set point is given 73.5 centigrade. P0 is given the 50% and P is given 55%. So here we have to find out the EP, that means proportional offset for the Kp is equals to 0.1, 0.7, 2.0 and 5.0. So now we start procedure. For the proportional controller, we know P is equals to Kp into Ep plus P0. So we can write Ep is equals to P minus P0 upon Kp. So we have the value of P and P0. So we get the Ep is equals to 5 upon Kp percentage. Now we substitute one by one value of the Kp. So for the Kp is equals to 0.1, the offset error is equals to 50%. Now second one, for the Kp is equals to 0.7, the offset error becomes 7.1%. And when Kp is equals to 2.0, the offset error becomes 2.5%. Same as when Kp is equals to 5, then at that time offset error becomes 1%. So this is the result for the different value of the Kp. It can be observed from the result that as proportional gain Kp increase, the offset error decrease. You can observe. So in this lecture we discussed about the proportional control mode. Thank you.